we heard quite a bit about use of quantum technologies, quantum computing, for solving some of the vexing problems in sustainability. For example, better efficiencies in fertilizer production or batteries. We heard a lot about using quantum for transportation systems and many of the other applications. And this session, we will focus on quantum for sustainability from the perspective of the UN sustainability goals, as well as then if quantum technologies do become mainstream at some time in the future, then we should be thinking from the outset about the sustainability of quantum technologies themselves, so that we don't make the same mistakes as sustainability being an afterthought in the communication technologies that we see today, which have been putting a lot of pressure on the climate issues. So with that, I want to introduce our newest assistant professor in electrical and computer engineering, Nivedita Arora. And she comes to us with a background in sustainability of conventional technologies. And after arriving here, we've been brainstorming about sustainability of quantum technologies. And she's going to give an overview of the landscape here, sustainability, quantum for sustainability and sustainability of quantum, and then we will have a panel discussion after that. So, floor to you.
Hello. Yeah. Thanks, Prem, for the awesome introduction. And also, the idea today is not so much to present any research finding, but ask some open questions about where the field is and just tease apart the topic a little bit more. So I have a little bit of a bad news for... Why is this not working? Okay. So I'll start with something which is not so good. Our planet is in danger and climate change is real. And in 2015, there was a group of approximately 200 countries which got together and signed a commitment towards looking into climate change, and that promised that we will try to keep the global warming to approximately 1.5 degrees Celsius in comparison to pre-industrial era times. This was called Paris Agreement, you might have heard. So if you look very closely, the blue region is where we are currently going forward, and by 2100 we will reach 3 degrees Celsius, and even by 2030 we might be hitting 1.5. And for the lack of better explaining, every 0.5 degree is very, very important. It leads to lot of millions of biodiversity getting extinct. There is hurricanes which would happen. There are forest fires which we are already seeing. There are island countries which would get underwater. So the next decade is going to be very critical about how we are looking into decarbonization and what are the solutions which we are adopting. So what we need is radical decarbonization efforts, and potentially if we look at how currently the sector and the global greenhouse emissions are there's no surprise that electricity, transport, and manufacturing are the main reasons, because are main contributors to it. And a lot of decarbonization efforts in carbon capture or low energy manufacturing of different chemicals or manufacturing techniques have been happening from the material science and chemistry fields. And what we basically would be needing is to accelerate these efforts. And this is where computing comes in more seriously. And a lot of these problems are search problems or optimization problems. And that is exactly what quantum computing is great at, to be able to solve these bounded error quantum polynomial time class problems, which are part of these NP hard problems. So consider a large optimization problem, which there was a lot of conversation, which both Bob and Hani talked about. Consider a large network of problem, and you have millions of input variables and what quantum could potentially do is to solve them in polynomial time. So what we are looking at is, we have just to give a perspective, quantum could solve our planet's problems, or I would like to compare this to how mRNA research was for COVID, is similarly what quantum computing could be for climate change. And this is a huge statement to say, but this is why we need to be innovating fast. And yes, we have made exponential innovations in the past decade with, we started in 1998 with 2 qubits, and now we are at almost 1,000 qubits, not just in terms of physical qubits increasing, the quantum volume of the qubits have also been increasing. There was a recent result which QEDC gave where we were able to have 48 logical qubits with quantum error correctors. So, but the question still remains, even if there are exponential advantages which are happening, what can quantum technologies do in the near term for decarbonization? We can look at it with an example of battery simulations. So, batteries generally are very important for, as we move more towards renewable energies or electric vehicles, their performance is really important. So when we try to look at battery, we do not need to really solve for millimeter scale, whole battery simulation to be existing. What we can actually do is to be able to solve more of a nanometer molecule simulation problems in the start of it. So starting with singular materials, for example, there have been recent results where strontium vanadium oxide, which is a cathode material in the batteries, has been able to be simulated with reasonably amount of qubits which are available today. So one of the things which has been a common learning point is that quantum computing people need to be working with domain experts to figure out impactful near-term problems, and also take that domain knowledge back into quantum algorithms, which could potentially actually result in reducing the number of quantum qubits which are required for doing the simulation. So that was also one of the learnings which has been happening. Further, if we look at other type of near-term decarbonization opportunities, there is power grid optimization. As we move towards more renewables, what we would be doing is, rather than generally coal is more central, is more a central network or hydroelectricity, but once you have these smaller renewable resources there, you'll split out your network into smaller particles, which you can see. So what you would have to do is to be dealing with these large optimization problems with lot of millions of inputs and power on resources going in and out. So there have been very interesting recent results where someone using D-Wave basically split out a German power grid, being able to show that you can create these 50 cliques out of it. There's very awesome collaboration with NREL and Atom Computing are doing together to be able to show how you can do switch power between different renewable and non-renewable power sources. It could be used for creation of new materials, of building heat is a huge issue where you lose almost 10% of the world's global energy is used for maintaining building temperatures. So thinking about how new materials could be manufactured, and also we didn't talk a lot about sensing till now, but yes, you could put use not just for decarbonization efforts, but also for measuring the climate change. You can use quantum gravimeters to be able to measure small changes in the environment, to be creating much more efficient climate models to understand climate change. This was the first part where we are focusing on why and how we need to be focusing on quantum for sustainability. But if we are going to grow quantum, which we are, there is no running away from it. So we should be doing it from a sustainability first approach. And But the question is this the right time? And we do have some arguments, and we can all discuss if that's the right kind of arguments. But it's very important to learn from history. And if we look at history, then whenever we have tried to build a technology, and we have mostly as technologists gone as performance first and functionality first, we tend to create these legacy technology flaws which take a long time to mitigate and first discover and mitigate. One of the very examples was like this very extensive use of DDT, which was there in the 1950s and 40s, and then it was this miracle chemical which could solve all your pesticide problem, but it really was resulting in a lot of health issues and was finally banned. Even though computing's been there since the 1940s, it was only, building from personal mainframes, personal computers to even, it was only till like 2000 when there was Electronic Waste Recycling Act, which was passed, or even for data centers, the first time there was, there was some guidelines given, your data centers need to be more power efficient only around 2007. This is pretty late. By that time, we have already sunk in and created our infrastructure in ways, and now it is too late to be able to changing them, and those habits get formed. Similarly, for satellite, now we are looking into space debris or security, which is also pretty much like how sustainability is treated like a second citizen. Security used to be treated like that. So security also, similar issues are there. So takeaway is sustainability needs to be a forethought, not an afterthought. Seems like beating a drum, but yes, we cannot be making things just from functionality and performance perspective. And when we consider the footprint, we need to be considering it from the complete life cycle, starting from production, like how we use the technology, and as well as what is the disposal of it. So in life cycle analysis, there are two terms. One is called embodied carbon, which basically tells you, and second is operational carbon. Embodied carbon basically deals with like how you are producing the whole hardware in itself, starting from mining, transportation of it, building the whole hardware, and then second part of it is what happens to it at its like at the end of its life cycle. So when we consider specifically for quantum technologies, there are a lot of rare earth metals which are used, as well as if you're using superconducting or other, then there is helium-3 and helium-4 which are used, which are potentially needs to be looked at much more carefully when we are producing. A lot of these rare metals are actually in these indigenous landslides where laws need to be put more sustainably. And another thing which we can do is to leverage existing semiconductors and learn from them how they have been doing it. And in terms of disposal, we can create modular design, think about how do we create refurbished markets. For example, currently quantum computers cost like millions of dollars. Some parts which probably IBM or Microsoft is using could be refurbished back. And how do we do responsible obsolescence? And in terms of operation, there's a lot of different type of architectures which are there, but how do we create energy efficient operations? Quantum supremacy does not really mean quantum climate supremacy, which basically is we need to be able to figure out if I am implementing one algorithm on ion trap or neutral atom or superconducting, which one of them would be the right kind of architecture to be implemented. IBM is already starting to put at their data centers, which part of the world they're putting, are they good resources for to be run by renewable resources? Can you make them net zero eventually in the future? And one of the most important things is like all quantum computers are basically having cooling and vacuum technologies which are used. How can you make it in low energy form? So some takeaways and thinking points, and we will potentially be discussing this during more in the discussion section, is like we need more energy and carbon benchmarks for quantum computers and to be able to decide our architectural decisions. Sustainability of quantum is not independent of sustainability of traditional CMOS or optoelectronics. Whatever we have done, even our legacy mistakes from there would potentially be carry forwarded. So we need to have a good look at both of our sustainability of traditional computing, but also sustainability of quantum together. And initially, we might have to do some initial investment for some of the applications for growing quantum. But eventually, all of them can pay out. For example, if we build a quantum computer which is able to solve the Haber's process in the next 10 years, it is a good, worth it carbon footprint investment, which would all pay out. So we need to be looking into a broader long-term pictures. With that, I'm going to leave with this call to action to the community. We have to be thinking from a complete life cycle, complete computing quantum stack perspective, including academics, industry, funding agents, educators, and policymakers all working together to push that we need to think about sustainability as one of the first principles because we have seen what we do to the environment in general. And with that, there is a QR code for you to follow and actually fill in if you are there interested to help us to contribute to it. And then I will give back Prem for future discussion.
Well, thank you, Nivedita. That was an interesting and well thought out introduction to the topic that we want to discuss. And we've assembled here 3 panelists. And so as you take picture of this QR code, this is, as she said, it's a call to action. If you can contribute, whether you have an expertise in algorithm development for sustainability, that is, if you are optimizing, let's say, how batteries work, how to make them efficient, and can help join the cause, then please, take that QR code and get in touch with us. Or if you are working on making the current quantum computing technologies more sustainable from their use perspective in future applications, then, so that we can create technologies that we will not have to come back and reformulate their manufacturing, for example. So with that, I want to turn to our panels. Mike Wasilewski, Director of Trinan Center for Sustainability and Energy at Northwestern. I'll have him say a few words about this topic.
Yeah, I mean, one of the, as Director of the Trinan's Institute for Sustainability and Energy, one of our major goals at the university has been to incorporate in all of the activities we do, areas that go far beyond science and technology, because we've always felt that unless you understand economics, public policy, and regulatory issues, then none of this wonderful science and technology is actually going to be incorporated into society. All of the quantum technologies need to be economically viable. They need to be publicly acceptable, and public policy comes into play in that field. And also they need to be controlled in the sense that, or uncontrolled, as the case may be, as the need arises, by appropriate regulation that doesn't inhibit technology development, but at the same time protects the community from any adverse activities that may actually result from this technology. So the whole package is really what's important for developing quantum technologies. And so I think from an Energy and Sustainabilities Institute kind of perspective, that's the kind of